Good evening, everyone. Welcome to today's KWK talk. Now I call upon our director, Dr. Guru Prasad, to welcome you all formally and also introduce the speaker.
Respected speaker of today's KWK talk, Professor Girish Kulkarni, other members of ICTS, and ladies and gentlemen, and my colleagues from uh, Jain Planetarium, and my young friends who are so interested in this talk. It is naturally exciting. Look at the topic today. Before that, anyway, this is a joint program organized by International Center for Theoretical Sciences, Bengaluru, as well as Jain Planetarium. On behalf of both the institutions, let me welcome Professor Girish Kulkarni, as well as all of you to this program. Excuse me. So, as I told, today's talk is very interesting. The title itself is indicative of that. 3 puzzles from the first billion years. So I had read a book, at least the title, The First 3 Minutes. Okay, Steven Weinberg, I think, if I'm correct. Okay, all of us are interested to know about the history of the universe, the origin and evolution of the universe and such. I'm not a person here to give you a talk. But anyway, suffice it to say that we are very fortunate to have Professor Girish Kulkarni to come and give a talk, popular talk here. Let me introduce Professor Girish Kulkarni. He's basically from Maharashtra, and he had his PhD from Harishchandra Institute, Research Institute in Allahabad. Later, he was a research associate in Harvard. All of us know where is Harvard. Heidelberg in Germany, as well as at Cambridge. All of them are very renowned institutions. I need not have to emphasize on that. And his topic of his talk and his interests are as interesting as his academic career, okay, and professional career. And he's basically a cosmologist interested in the history of the universe, especially the early universe. Okay, at least astrophysicists like Professor Girish Kulkarni say, and people like us nod, that, first there was no light as such, universe was very dark. Later, okay, there was first light formation of stars and galaxies. Anyway, one of them is the 3 puzzles from the first billion years. In the first billion years, so many things happened. He's going to elaborate on that. So if I were to tell you, first thing is the formation of the stars and galaxies, so interesting. Then the ionization of the intergalactic medium between the galaxies, how ionization took place. And third thing is more interesting for kids, okay? Formation of supermassive black holes in the core of the galaxies. So how all these things happen, how they influence the later evolution of the universe. These are the things he's going to speak. Anyway, I don't want to be between you and Professor Girish Kulkarni. Once again, I welcome him on behalf of ICTS as well as JNP. Sir, the stage is yours. Please.
I also request Sir Guru Prasad, sir, to hand over a memento from ICTS.
Okay, I hope I stand up to that superlative introduction. I should thank Dr. Guru Prasad ji for this really warm welcome. We just had an amazing chat about his career and his amazing contributions to Indian space program as well as to scientific outreach. It's really nice to be here. This is my first time speaking to a Bangalore audience, and I realize that there is an RCB game going on right now, so I should be doubly thankful for all of you showing up here this afternoon. And I guess I should also thank ICTS for inviting me to speak. Disha has been handling all the logistics really well from there. So the plan I have for this talk, as Dr. Guru Prasad told you, is to introduce you to these three problems in the first billion years of our universe, on which very active research is being done in India. I want to give a sense of what's happening in India and what we are trying to do these three problems. So the agenda is to understand what these three questions are and then to get some feel for what we are doing. The audience is very mixed. There are small children and college-educated adults. So I do hope that I manage to make sense to, at some level, to all of you. But feel free to ask questions at the end of the talk if there's anything that's unclear. So many people actually know what astronomy is, but not many people understand what cosmology is. So I think I should start by explaining what this field of cosmology is and what we do when we say we do cosmology. So the idea is that we know if we go to a dark enough sky, I don't know if Bangalore kids get to see, they probably have to come to the Jawaharlal Nehru Planetarium. But if you go to a dark enough place and you look at the sky, it's beautiful, full of stars and so on. Now, it's actually often very hard to imagine and appreciate how big this space is, which we see in the night sky. And so if you look at the same patch of sky using a very powerful telescope, and we do that using the James Webb Space Telescope, if you look at a very, very small part of the sky, very tiny corner of the sky, what you see is something like this. This is an image, this is a photograph taken using the James Webb Space Telescope of a really small patch of that night sky. How small is this patch? It's basically covering just 1/3 of the disk subtended by the full moon. You know the full moon? And it's just a small fraction of that area. And what you see here is a volume which is billions upon billions of cubic kilometers. And every little dot here is a galaxy which contains trillions of stars. So this is huge, right? There's this, I don't know if Bangalore people read Douglas Adams, and his famous line in his novel is space is big, mind-bogglingly big. And it's really, really big. And what cosmologists do is they try to do science at this very, very large length scales. They don't do science at the meter scales, the scales of chairs and tables and humans. They don't do science at the small scales of atoms and molecules. They do science at the hugest scales, the scales of the universe. Okay? What are these scales? Just to put some numbers. So we know the distance from the Earth to the Sun is about 10 to the 8 kilometers. That's 1 followed by 8 zeros. How much is that in billions? I think 0.1 billion, 100 millions. I can't do millions and billions in my head. But it's a very large number, and it's called astronomical unit, as some of you frequent visitors to the planetarium will know very well. About 1,000 of those gives us a light year, the distance that light travels in a year. About 1 million of those gets us a megaparsec. That's already pretty large. And what cosmology does is it does astronomy at the scale of 100 megaparsecs or 10,000 megaparsecs, about 10 gigaparsecs. Okay, so this is very large. In fact, one might ask, what's the point of studying these large scales? And good people have answered these questions. Subramanian Chandrasekhar thought about this. In 1960, in his diary, he maintained a diary of his, while he did his research, he penned down his thoughts about his research in a little notebook, which is published by his wife, Kamala. And now he writes there, granted that physical science as a whole is worth pursuing, what is the particular case for astronomy? Astronomy here, but this argument is doubly valid for cosmology. And he says, my own answer is this. Nature exhibits different patterns at different levels, and the patterns of the larger scales are what needs to be studied, and the only way to study them is cosmology. Indeed, what you can study in cosmology, you cannot create in labs. The only way to study it is these very large scales. So what are the questions that we ask? What we try to ask is, how did the universe form? When did it start? When did it begin? What is the age of the universe? What does the universe contain? Does the universe change at all? How does it change if it does change? What will happen to the universe in future? These are the kind of questions that cosmologists lose sleep over. Okay? And in fact, it's pretty, if you think about it, it's actually quite remarkable that this human brain is capable of grasping these really, really large scales. I can grasp meter scales because I need them for my survival. I need to understand hot and cold. I shouldn't require a physics PhD to understand hot and cold. But why the hell would my brain be equipped to process these very large scales? And indeed, just 100 years ago, cosmologists were considered crackpots. And Ernest Rutherford, the great atomic physicist, is the head of the physics department in Cambridge, hated them. He said, don't let me catch anyone talking about the universe in that department. In fact, if you read the kind of research that they were doing in cosmology, it was like numericist research. Maybe I think there are these many atoms and this many, so maybe the universe is, there's no science really. But now, since 1925 till 2025, cosmology is completely transformed. If Rutherford were alive today, he would probably be a cosmologist, because cosmology is now a really precise part of astronomy and physics. In fact, we understand things about the universe more accurately than we understand things about this room, right? And how has this happened? The process I want to convey to each of you is that the way cosmologists work is like an archaeologist. The way an archaeologist digs the earth to find history of a place, that is exactly what the cosmologist does with the universe. Cosmologist digs layers of time away from the universe. This is perhaps a way to explain this. You have a very nice city and you want to ask, well, what was here 100 years ago, 1,000 years ago? The archaeologist is going to dig under the earth. Maybe they'll find some buildings like this and they will infer so and so people used to live here, this is what they used to do, all with some error bars and uncertainties. Luckily, this is exactly what you can do in the universe thanks to the finite speed of light. Light doesn't travel at infinite speed, light travels at a fixed speed. So things that are far, you are actually looking back in time at them, right? When we look at the moon, we are seeing the moon as it was a second ago. When we look at the sun, we are looking at the sun as it was 8 minutes ago. When we look at Mars, we are looking at Mars as it was 12 minutes ago, right? And similarly, when we look at faraway galaxies, we are actually looking at the universe as it was billions. So the universe comes fitted with a time machine. All we have to look at is these faint and faint objects, and the fainter we go, the backwards in time we go. So this is the cosmologist's archaeology. In fact, you can now apply this to that night sky that I showed. You build better and better telescope, look at fainter and fainter objects, and what you are going to do is look at the universe at these larger scales. Okay, so people have done this over the last 100 years, and what did they find? Well, the first thing that they find is that this thing is full of galaxies, as we saw, just different kinds of galaxies. So cosmology at the start was just this zoology of picking up collections of galaxies, round galaxies, egg-shaped galaxies, red galaxies, blue galaxies. But then cosmologists became better and better, and they built telescopes to measure millions and millions of galaxies, and then they could chart a structure of the universe. And this is what came out of that. This is the famous Sloan Digital Sky Survey, which was a very ambitious project that was done for a period of 10 years. Each point here is a galaxy. And this is a map of the universe around us. And what you see here is they are not random. There is a structure. And in fact, we can now measure this structure mathematically. What I'm showing here is a photograph, but you can actually measure this structure mathematically. And the absolute remarkable thing is we can use physics to explain it to extraordinary precision. I can actually sit in my drawing room and predict that structure without ever having to go to a telescope. And that's the grand success of cosmology from Rutherford's time till now. So what is this success? What have we learned about the universe since then? Well, the first thing is that the universe fits the famous Einstein's theory of gravitation. Okay, so this is the famous Einstein equation. What those of you who have done physics might recognize it. I've just put it for ornamentation. I'm not going to discuss it at all. But then one of the interesting things about the Einstein's equation is that it immediately tells us the geometry of something. Okay? So immediately we have a geometry of the universe. It has a name. It is called the FLRW metric. No need to worry about what it exactly means. Essentially, it boils down to saying that the universe is flat, a bit like this room. If I draw X, Y, Z axis, the universe looks like a cube. Not like a saddle, not like a ball, but looks like a cube. This might sound like a trivial point, but this has taken millions and millions of dollars to prove that the universe is actually box-like and flat. In fact, there are colleagues here right now at ICTS who will fight with me about how flat it is. But more importantly, universe is not just flat, but it's expanding. Galaxies are moving apart, away from each other. And really amazingly, this FLRW metric says the fact that there is FLRW immediately puts an age. FLRW has a t equals 0. It says that the universe was born at some point. It did not exist at some point, and there is a starting point, and the age today is 13.8 billion years. I hope you appreciate the precision that we have here. Now, Einstein's theory doesn't just tell us about the geometry, it also tells us what the universe contains. Okay? So what are the constituents of the universe? We know what that is as soon as we apply the Einstein's equation to the observations in cosmology. It says that the universe has ordinary matter, the things that we are made of, atoms and molecules of various elements that we study in chemistry. But it also has something called dark matter that we don't know what it is, doesn't seem to be the thing that we are made of. It also has light, the normal light that we see, but not the light produced by these electrical lights or the sun, light produced at the birth of the universe. And then finally, it also has something even more bizarre called dark energy, which also we don't quite understand what it is, but we know that it exists. Okay. Now of this, we only see the ordinary matter. That's the thing we can point fingers as this is ordinary matter. The rest we just infer from these observations. And what is this ordinary matter? Most of it is just hydrogen. Then the rest of it is helium, and then there is tiny, tiny bit lithium, nothing else. All of the rest, the oxygen and the carbon atoms that make up our body, were produced by stars later. They were not produced by the universe, they were just produced by some star. These atoms were actually part of some stars that were thrown away when the star exploded. Now this whole story is what has been developed in the 100 years. Just imagine the amount that we know. This is all textbook material. This is all what you are supposed to do when you start a PhD in cosmology. So it's that traditional now. There's nothing new about this. And this has a name. It's called the lambda CDM model. That is the Greek letter lambda. And this lambda CDM model is our current description of the universe. But this is not all. What actually amazes me is the next bit, which is included in the lambda CDM model. It says that this metric that we have, this shape that we have, this geometry that we have to the universe, it's not smooth. It has very tiny, tiny ripples on it, small perturbations on it, okay? Like those on this curtain. Who created, what created, we don't know yet. That's the bit that's not known yet. But the fact that these perturbations exist, we know very well. And these perturbations, what's amazing is that as soon as we apply our understanding of physics to these perturbations, we can show that they grow and produce exactly the cosmic web that I showed from the Sloan Digital Sky Survey. So this really does reproduce the universe that we have seen. In fact, here is one effort by a few people at an American university, where you can see they start with these small perturbations and then they grow them on a computer, and you can see the pattern that is emerging is very similar to the pattern that was seen in that diagram that we saw at the beginning, right? In fact, you can show it quantitatively here. I'm just showing at a visual level. So that's the plan. What cosmologists do, they go to the telescopes, they make observations, they get these data about the night sky, and then on the other hand, they build theories. You have your pet theory about what dark matter might be, what might have happened at the Big Bang. They will compute that using the laws of physics, and then that is called a model. And then finally, the model and the data are confronted with each other, and what comes out of that is called inference, which is the insight about what the universe contains. That is how the information about things like the age of the universe and the shape of the universe is obtained. Now, this whole thing has been extremely successful, and a string of people have won Nobel Prizes for all these discoveries that I told you. By my count, there are at least 4. I was talking to someone last night over dinner, and they said there are 6, but we disagreed whether that's really cosmology, so I don't know. But all of these people were responsible for developing the story of cosmology in the last 100 years. Just to continue with this archaeological metaphor for just a bit, there's one interesting twist in the cosmological archaeology which I just want to mention. It's slightly tricky, so let's see if I can explain it. If you look at archaeology, your topmost layer is this modern city, which can be compared in the universe with full of galaxies and things that exist around us in today's universe. Then you dig a bit and you find some archaeological ruins, but they are still pretty structured. This is like looking at that cosmic web a bit farther away from us. Then you go a bit below, and then you find very faint broken ruins. This is like very old galaxies. Then you expect some sparse bones. No, nothing is left at this very deep layer of the Earth. This is like really, really far away stuff in the universe. And then finally, you don't expect anything. That's the typical thing in cosmology, in archaeology, right? So if I drew a diagram like this, where on the horizontal axis I have time, I would imagine that today, when the universe is 13.8 billion years, you will find that our understanding of the universe is really good, but the quality of our understanding of the universe degrades as we go back, just as the archaeological quality degrades as we go deeper into the Earth. Now, what's remarkable is there is a twist in the story in cosmology, which is just before the last layer. Imagine that in that archaeologists digging up, suddenly there was a layer where there is an extremely well-preserved city, beautifully intact, with buildings and walls and everything, all documents and artwork and everything. Imagine that you are going in, things are degrading, and then suddenly there is a layer where everything is intact, and then again there is nothing. Bizarre, isn't it? But that's exactly how it is in the universe. In the universe, there is one layer really from far back. How far back? When the universe was just 100,000 years old. Around that time, somehow, luckily, fortunately, didn't have to be that way. Somehow, that moment is available for us to see today. Okay, thanks to something called a CMB, Cosmic Microwave Background. Just a name, no need to worry about what that means. It's just called a CMB. These are the observations. If you build a microwave telescope, this is what you see in the sky. In fact, I don't know if people have looked at these old televisions. We used to have them when we were small. When the TV is out of tune, you had these dots, the black and white dots shuffling on the screen. We used to call them ants on the TV screen. I don't know how many people are as old as me here. Part of them are these photons from 100,000 years ago. These are the photons that you are seeing on your television screen. Okay. What's remarkable is the observations of that light from 100,000 years is so precise that at that point we have an extremely good source of information of the universe. So this is how the situation is in cosmology, that we have some high quality data today, and then the data degrades, and then at some point suddenly bizarrely, we have abundance of data. We have almost everything we want to know about the universe on that day we know, and then there is a gap again. So what people like me do today, today's cosmologists, they try to fill this gap. So this is all I do day and night is try to fill this gap so that 20 years later I can come to your planetarium and show a plot where there is no black color here. Okay? And so that's the first billion years. First billion years is this period of the universe where our observations haven't reached yet. Now you might say, okay, the observations haven't reached. They will reach, just wait, technology keeps improving, which is correct. The mind-boggling thing is somehow, bizarrely, there are things here which somehow are only explained by some mysterious things that happen in that gap. It's unfortunate that happens, but it almost feels as if unless I quickly fill this gap, I'm not going to understand what happens here. Okay? There are three such things. And so those are the three puzzles I want to highlight in today's talk. There are three such things which we think must have happened here, but we don't know. And unless we can explain that, things here don't make sense. Okay? So that's the agenda. So here's puzzle number one. Okay, the puzzle is, when did galaxies form? All of us know galaxies. Okay, even the youngest members of the audience have seen galaxies as photos on the internet. I don't know how many of Bangalore people see the Milky Way in real life. Probably it's not possible anymore. I wonder how far you have to go from Bangalore to glimpse the Milky Way, which is a pity, but whatever. That's a price for development, I guess. But the idea is, we actually don't know how galaxies form. These galaxies that we see, we know how stars form. We have actually seen stars form. We have seen stars die. We have never seen galaxies form. The universe is full of galaxies. How the hell did they get there? We don't know, right? Now, people worried about this. People said, okay, we've got the cosmic web, all those small ripples, you managed to show that pattern, but did you get what exists on that pattern? Did you get these spiral objects with gas and stars? That is a problem. And people started worrying about this, and they said, okay, we can start making some theories. Maybe this happens, maybe that happens, maybe there is some gas coming this way and that way, and maybe once you do that, you get some formation of stars and galaxies. And that was the grand start of a field called galaxy formation. And a pioneer of that was this great man called Jeremiah Oestreicher. Okay. Jeremiah Oestreicher was a professor at Princeton University, and after retirement, he spent time in Columbia University. And he's the one who first made an attempt to understand how galaxies might have formed. And I'm particularly happy that I have occasion today to mention his name, because he has three interesting stories, which I think will interest you. So first is, he was Chandrasekhar's student, Subramanian Chandrasekhar's PhD student. He was a great person. He was very kind and supportive. I myself have benefited from encouragement from Jerry Oestreicher. He used to make it a mission to support all young researchers worldwide. Second thing is, he passed away just last week, last Monday. Okay, so very, very sad loss. And the third thing is, he has a remarkable story about Bangalore, which is that he invaded Bangalore without a visa. Jerry Oestreicher was a very spirited person. I don't know if people know this New York Jewish personality. Nothing defeats them. And he arrived in India to visit the Raman Research Institute in Bangalore. He landed at the Mumbai airport. And then, of course, Americans don't need visa to travel to many countries, so they are not used to this thinking that a visa is required. He was told at the Indian border on the Mumbai airport that you need a visa. And he didn't have a visa, and the guy made them sit, Jerry and his wife. While the fellow went inside to talk to his boss, what should we do to this American professor? And this was before these fancy gates that they have, which you can't cross now, the alarm started beeping or something. And Jerry Oestreicher just tore his custom perchi and walked in. Not just did he walk into Mumbai, he then traveled all the way to Bangalore. And then the director of the Raman Research Institute at that time was Radhakrishnan, Rad. I don't know if you know, he himself is a great personality with many stories. And Rad had to make phone calls to Delhi to just avoid him getting arrested. So this was Jerry Oestreicher. And Jerry Oestreicher built this picture, which by now many people have made very sophisticated, about how the gravity and physics of fluid dynamics might end up creating these galaxies that look like. So it's not fully built yet. The picture, the work that Jerry Oestreicher started is not done yet. But the critical ingredient in that theory is that at some point there were no galaxies. At some point the first galaxies formed. That is required for galaxy formation, right? The problem is we still don't see galaxies form. In fact, this is one of the highest redshift galaxies. In fact, until 2 weeks ago, this was the record holder. Now we have an even farther galaxies known. You can see in this little square here is this speck. You can see still pretty galaxy-like object. And this is at what we call redshift 14. So this is what, 13.3 billion years away, billion years ago. This is right near the Big Bang, and there still are galaxies. So how did these galaxies form? They must have formed here, because we know that the CMB has no trace of galaxies, right? So it's critical that we find, otherwise our whole lambda CDM model is on shaky foundations. Indeed, many James Webb Space Telescope programs are trying to find these primordial galaxies. But the question is, what if they are too faint? And this is where I want to describe a bit the work that we are doing, which is there in 1977, two Russian folks, Varshalovich and Khersonsky, if my pronunciation is okay, they said, okay, to find these earliest galaxies, to find the moment when galaxies formed, don't look for galaxies at all. They had a completely different idea. What they said was, well, look at your CMB. Don't look for galaxies, just focus on your CMB. We know that the CMB is forming in an epoch before galaxies. So this CMB light is traveling to us through the period when galaxies was formed, right? Now what they said was, well, most of the universe is hydrogen. And what these two Russian people found was that the hydrogen atom has a certain structure which makes it possible for us to detect the formation of galaxies, detect the moment the first galaxies were formed inside the CMB. Pretty remarkable. Okay, so what they said was, so I didn't expect too many children to be here, so I apologize if there is a bit of technical information, but for those of you who are interested in careers in physics, maybe I'll quickly say, because this is just really fascinating. What they said was, if you look at the lowest energy state of hydrogen atom, that itself is split into two energy states which are separated by a tiny amount of energy. The problem is, we can actually use statistical physics to count what fraction of the hydrogen atom in the universe lie in this lower energy state versus what fraction lies in the upper energy state. Now, here is the amazing thing. When most hydrogen atoms are in the upper energy state, they don't do anything to the CMB. But when they are in the lower energy state, they are in a capacity to absorb CMB and produce a dent in the CMB spectrum. Okay. Now the problem is, most hydrogen atoms are usually in the upper state. But what these two Russian people showed, amazingly, is that the light from the first star, which is very different from the light produced by Big Bang, is the first thing that can pull these hydrogen atoms down. That and only that can bring hydrogen atoms down to the lower energy state. Can you imagine how amazing this is? That these galaxies, which have nothing to do with CMB, happen to be the only thing that can pull all hydrogen atoms to this lower state. And as soon as you bring them to the lower state, you see a feature. So here what I have shown on this plot in the red is that fraction of hydrogen atoms in the upper versus lower state in some units. Essentially, when this red curve is high, most hydrogen atoms are in the upper state. When the curve is low, most hydrogen atoms are in the lower state. And what you see here is that as soon as galaxies form sometime around this point, this is just a theoretical calculation, this is not real data or anything, you see that as soon as the galaxies start forming, this thing is pulled down. And as soon as that thing is pulled down, you get this little dent in the CMB spectrum. The CMB spectrum normally would have been a straight line here, it's subtracted out here, and so because galaxies form, you get this little dent here. In fact, a brilliant PhD student in my group, Shikhar Mittal, who is now a postdoctoral researcher in Cambridge University, has recently done the most sophisticated calculation of how these galaxies affect those hydrogen atoms. Okay, I won't bore you with the details, except that people are trying to detect it. So there is this group in America who built a little telescope. This is actually a telescope. What happens is that the feature that you are trying to detect in this CMB spectrum is at radio wavelengths. And it's everywhere in the sky. So all you need is a radio telescope which can see the whole sky at once. And this is just a metal piece. So the thing in your mobile phone or your TV antenna will detect this, except that you need to calibrate it really, really finely. And so this is just a piece of metal which is calibrated really precisely, put in a place where there is very little radio emission from mobile phones and TV. So this is Western Australia. And the amazing thing is, in 2018, they claimed that they found this. So this, they claimed, was their discovery. So this was very groundbreaking. This was, we really spent 2 weeks without sleep to investigate these data, and we found a lot of issues with it, etc. I won't go into that story here, except that the race now is to confirm this. And I should highlight that the Bangalore astronomers are at the forefront in India. So Saurabh Singh from Raman Research Institute has built a wonderful telescope called Saras, which sits on this lake in near Gauribidnur in the Chikballapur district, where he is trying to detect the same signal of galaxies forming. And in fact, he has published a result in 2022 disagreeing with the EDGES result. So he doesn't see anything. So we have a very interesting conflict between Saras and EDGES. And in fact, another group in Bangalore, Mayuri Rao, has now proposed an experiment where this telescope will go around the Earth first and then around the Moon. She has called this Pratush, and ISRO has now funded the preliminary sort of steps of this. At some point, there will be a telescope flying, and when it's behind the Moon, it doesn't see the Earth at all. So there is no problem with pollution from man-made radio signals. What am I doing? If the Bangalore people are doing all the fancy, what are us Mumbaikars doing? Well, we are also doing something. This is the telescope that me and my friends have built in the desert of South Africa. We call this REACH, Radio Experiment for the Analysis of Cosmic Hydrogen. And the hope, it is taking data as we speak. And so hope is that maybe at some point I can tell you that we have seen how galaxies form. That's the puzzle number one. This puzzle number two, how did black holes form? I was told that this is a hot topic for all young friends in the audience. This really is really fascinating, actually. And so the story here starts from 1963, and here the person to mention is Martin Schmidt. He also passed away recently, just a couple years back. He was a professor at Caltech, and in 1963, what he did was he used a telescope called the Hale telescope and pointed it out at the stars in this little patch of the sky. This happens to fall in the Virgo constellation. And he just observed each of these stars one by one. What he found was this particular object. It looks exactly like a star. There is absolutely no reason for anybody to doubt that it's a star, except that what he did, he put a spectrograph, a prism, on his telescope and got a spectrum. And as soon as he got a spectrum, he was shocked, because this thing, the spectrum was not at all like a star. It was completely different. In fact, I won't go into the detail, but the spectrum allowed him to infer that this object was 2 billion kilometers away, well past the distance over which we see stars. Not only that, it was also flying away at a huge speed, 16% of the speed of light. So it was the fastest and farthest object around that time, and it made him a celebrity. He was on the Time magazine cover in 1963 or 65, I think. And this was really earth-shaking at that time. People thought, what have we found? And indeed, it has been a mysterious object ever since. Because by now, hundreds of thousands of such objects are found. Martin Schmidt called them quasars, because he called them their quasi-stars. They are stars, but not really stars, so he called them quasars. And we have now seen many. These are very routine. And there's a long story, but essentially we think that there is a black hole sitting inside them. And those who have seen Interstellar, the Hollywood movie, will know that black holes have this gas disk around it, moving at great speed. And because it's moving at great speed, it heats up and it starts producing light. How much light? Light enough to outshine the stars in the rest of the galaxy. Okay? In fact, later it was discovered that supermassive black holes exist in almost every galaxy known to us. Right at the center, there is this black hole. The mass of this black hole is equal to the mass of about 1 billion suns. These are huge. That is why they are called supermassive. Even our own Milky Way galaxy has such an object. It's in the constellation of Sagittarius. You can see the dust around it if you again go to a dark enough place, etc. In fact, they are ubiquitous, and if you had X-ray eyes instead of optical eyes, if you had X-ray eyes, the sky would be full of supermassive black holes. You will not see any stars because stars don't emit any X-rays, but this is how a tiny part of the sky would look like. This is an image from an X-ray telescope, and every dot here is a supermassive black hole. In fact, I have spent 5 years of my career building a very careful catalog of all supermassive black holes known. It turns out counting is very hard in astronomy. It took me 5 years to count these 80,000 objects here. Again, the problem is we never see these form. They are always there, ready-made, prepared, all mature. Where do these objects come from? We know where stellar mass black holes come from. Chandrasekhar got the Nobel Prize for it. Chandrasekhar actually showed how that is happening. Where do these supermassive black holes come from? In fact, here is a record holder. This is a field which was observed by the James Webb telescope and the Chandra Space Telescope. So the violet bit is Chandra, X-ray emitting gas, and the galaxies are all James Webb. And this little thing here has an object which is called UHZ1, which is currently the farthest object. It's about 13 billion years ago, and it's still a 10 billion solar mass black hole, fully formed, doing its thing. Now the problem is, as far as we can think, black hole only grows by feeding on gas and stars. It accretes, eats up gas and stars, and that's how its mass can rise. The problem is, even under ideal condition, they can't eat arbitrarily fast. They are not like us. They have a limit at how much they can eat. And this limit is called Eddington rate, because if they eat too much, then the light produced is so strong that the light itself pushes matter away from the black hole. So there's a self-regulation mechanism. So if we start from the kind of black holes that Chandrasekhar explained how to produce, we need some time to get to these billion solar masses. We can't just get there very fast. But then the problem is, at these very high redshifts, at these very early times, there is no time from Big Bang. There is barely 100, 200, 300 million years in which you want to get to 1 billion solar masses. So this means either there is something strange in our understanding of black hole formation, or they can actually eat too fast. They can actually accrete material too fast. So the puzzle here is, how did such a huge black hole form early? This is a figure from the paper announcing the UHZ11. I won't bore you with the detail, but essentially they are trying to say that there's just no way you can get up to the mass unless you do something strange. Yeah. Now, to explain what we have done on this problem, I actually first need to tell you about the third puzzle. So let's first talk about the third puzzle, and then I'll tell you about what we have done on the second puzzle. What is the third puzzle? The third puzzle is that of reionization. This is the temperature of the universe. It turns out our universe is very hot, and we don't understand why it's so hot. In fact, if you look at that image that I have been showing again and again in this talk, we have been highlighting the fact that there are all these galaxies, right? Millions and millions of galaxies, each containing about 1 trillion stars. The amazing thing is, in this photo, most of the matter is not in the galaxies. Almost 90 to 95% matter is between the galaxies where you can't see it. Okay, isn't that amazing? And this is called the intergalactic medium because it is between galaxies. And the reason you can't see it is because it's very diffuse, it's very thin. It's so less dense that it cannot emit any light. How less dense it is? If you construct a meter cube box in this room, it will have about 10 to the 24 atoms, one with 24 zeros behind it. Here, there will be one atom. It's 24 orders of magnitude less dense than the gas in this. It's more vacuumer than the extremist vacuum that any man has produced anywhere. It's 4 orders of magnitude less dense than the deep space inside the Milky Way between stars. So this is nothing. And as a result, it doesn't emit gas. But we know, in fact, there's a very famous paper in the 1950s by a French woman who showed that this is not empty. That in fact, most stuff is lying there, not shining at us. So how do we see it? It turns out that there is a technique by which you can see it. Not just can you see it, you can measure its temperature. So I'll quickly mention it. One way to see it is in absorption, by which we mean when this matter transits some bright object. So has anybody seen transits in this audience? You have 1 per 2, 3 person have, yeah. We have seen a transit together, Kaapi. Yes, there's wonderful ways of seeing transits of Mercury and Venus. So this is the transit of Mercury, where the planet Mercury passes in front of the sun. And now you are actually seeing Mercury only in its ability to block the solar light. You are not actually seeing light coming from Mercury. In fact, you are seeing absence of light where Mercury is. In fact, this is the only way I have seen Mercury. I have never been able to see Mercury as a bright object in the morning or evening sky. And so now what you could do is you could use this same technique to study gas in the intergalactic medium. Now, intergalactic medium is mostly hydrogen, as I told you. And hydrogen, unlike Mercury, can't block everything. It blocks light at a fixed certain wavelengths. Right? It has energy. Hydrogen gas is not a solid mass like Mercury. So these are these atoms which block light only at a certain wavelength. So slight twist in this setup happens. So for example, what will happen when you look at, if Mercury behaved like this intergalactic hydrogen, you would look at the sun at wavelength 1 and you would see the sun. There won't be any Mercury. You go to wavelength 2, suddenly you have that Mercury, the light is blocked, and then wavelength 3 again there is transparency, so that you again see the light. Well, exactly this is what we do to see intergalactic medium. You take a spectrum, you put a spectrum or a fancy version of it on the telescope, get a spectrum of it, and what you will see then is at some frequencies there would be nothing happening to the background light coming to you, but at some frequencies the light will be absorbed by this intergalactic medium, by this invisible matter between galaxies, and again at a third frequency nothing happens. Now the interesting thing is, the physics of this absorption is just quantum mechanics, and that responds to temperature. So if the hydrogen is at a different temperature, then what happens is that the absorption feature, the shape of the spectrum changes. You can use that to measure the temperature of the intergalactic medium. In fact, the setup that astronomers use is something like this. They find a really bright galaxy far away. This is usually quasars. Quasars are the brightest objects, as we just saw. And then you see this quasar using a fancy telescope and a spectrograph here on Earth, and the light that is coming to you from the quasar is traversing through these billions of kilometers of the universe, and the hydrogen atoms in this universe will do this. They will do what Mercury was doing to that sun in that photo. In fact, the result you get is like this. This is the quasar spectrum, and the hydrogen atoms around the sight line produce this absorption lines. If you have a high resolution spectrograph, you can expand these absorption lines and you can measure the temperature. This whole thing has a name. It's called Lyman alpha forest. Just a name, no need to worry about where it comes from. But when I say Lyman alpha forest, I mean this transition caused because of hydrogen. The amazing thing is that this tells us that the intergalactic medium is hot. This is what tells us that the temperature is about 10,000 Kelvin. What is the problem with that? The problem is that we also, of course, know the temperature at the 100,000 mark. Remember, we know everything at that point. It's that buried, intact city deep in the earth. And we know the temperature there, and it's about 1,000. And in lambda CDM model, as soon as you know it at one point, you know it everywhere. And it says here it should be 1 or 2 Kelvin today. What you see is 10 to the 4, 10,000. What happened? And the problem is, again, the first billion years. You keep measuring backwards in time, and every time you keep finding 10,000 until you hit the first billion year mark. The problem there is somehow, I wish the universe was not like that, this Lyman alpha forest technique stops working. Why it does, again, is unfortunate. There is nothing fundamental about that. I can go into the details of why it stops working, but in fact, it does stop working. In fact, if you look at the farthest quasars and calculate their Lyman alpha forest spectra, there is no forest, there is no absorption signal. What you get is this complete wipeout of the signal. There is nothing. There are no lines. It's like the mercury completely eating away the light of the sun. And then if there are no lines, I cannot expand them, I cannot measure the width of them, I cannot measure the temperature. So I just cannot figure out that the gas heated at some point. Okay. In fact, this is celebrated plot was made by a very respected astronomer from America, Shadowy. And over coffee one day in, I think, 2016 it was, he told me, Girish, I made this figure in 2006 and nothing has happened in reionization since then for 10 years. What is remarkable is just that year, we had really weird luck and we could solve this problem to some extent, really bizarrely. Just shows you how science works, because just around the time that Shadowy was making that depressed remark of having stagnated, there is a person called George Becker in the University of California at Riverside. Riverside is a very nice city near Los Angeles, for those of you who are familiar with California. What he did was, he looked at those high redshift quasars, these early quasars, where the Lyman alpha forest doesn't work, and he compared them. And he found something amazing. He said, the Lyman alpha forest changes quite a bit from quasar to quasar. Quite drastically, in fact. And the example he shows in his talks is these two quasars. So this is black curve here is the spectrum of one quasar. The red curve is the spectrum of a second quasar. These are the names of those two quasars. And what you see here in one quasar, the absorption lines can be seen. There is emission between absorption lines. But in the other quasar, there is almost complete wipeout. So he said, what's going on? Why is the universe so different in this direction than in that direction? He found that to be weird. In fact, what he did then is he put a number, he quantified it. He put a number, no need to understand what it is, except that when this number is large, the absorption is severe. It's like that red quasar. And when it's small, it's like the black quasar. There is a lot of transmission. And then he plotted this against time. Cosmologists measure time in a strange way, which we call it Z, and then it's small numbers. But it's essentially time. And he found 6 is the 1 billion year mark. Above 6 is the pre-1 billion universe. Below 6 is the post-1 billion universe. He said, look at this. All the quasars here have roughly the same value of the Lyman alpha forest. But as you go towards the 1 billion year mark, there is a huge scatter. In fact, the scatter is about factor of 500 here. So the universe changes factor of 500 from place to place. Around the time, what I was doing was, I was doing what theorists do, the modeling. I was playing with an idea of what might have heated the universe. I thought, okay, let's imagine that early galaxies had stars, and these stars produced high energy light, just like our sun does. And this light is what heated up the whole universe. There were so many galaxies, I thought, that they produce sufficient light to completely ionize and heat up the universe. So, and then we developed a GPU-based method to make a calculation, because then you have to solve for gravity, hydrodynamics, and radiation physics. It's an interesting topic of discussion. But then once you do that calculation in a computer, you get to develop a model of reionization happening. What you are seeing here is an artificial universe where on the well, right here is the temperature of the gas, where the blue are cold bits and the white are these 10,000 Kelvin bits. Again, this is just a hypothesis. We don't know yet whether this is truth. This is just Girish Kulkarni has cooked up this idea that, okay, I will make an artificial universe, I will put these galaxies, I will let the galaxies produce radiation, and then if I calculate that using known laws of physics, this is what I get. So this is the temperature, and you can see gradually universe getting heated up, and here is the ionization. At 10 to the 4, hydrogen cannot remain as an atom. The proton and electron split, so you have essentially free electrons and protons. And that's when George Becker's result came, that Lyman alpha forest changes a lot from sightline to sightline. So I said, okay, let's compare this. And my first reaction was this, which is, so this is a bit of a technical plot, but let us maybe focus on just this figure here, where what is shown is again the strength of the Lyman alpha forest, such that when this number is high, we are like that red quasar, too much absorption, and when the number is low, it's like the black quasar. And what is shown here is what is the cumulative distribution function, which means what fraction of numbers, what fraction of quasars are less than this number. So how many quasars have this quantity less than 2, less than 3, less than 4, less than 5, etc. And so the black here is the observation, and I compared it with my simulation, and they just didn't agree. And so, okay, this was, in fact, we gave talks at conferences saying something is wrong, we just cannot fit the data, we don't know what's going on. And then one day, it just worked. I still remember that morning when I figured out what needs to change in that model, and then it just fit the data. This is essentially the same plot, where the red are now the data and the blue are my simulations. You can see the match is perfect. And essentially what was required was the idea that reionization had to finish at a certain point. It turned out that if I changed that end point just a tiny bit, I cannot fit the data. This is the first time we figured out how the universe might have reionized. In fact, this artificial universe looks like that. Again, busy plot, but look at the middle panel. This is how the temperature evolves. So when we are at very early times, we have these individual galaxies producing regions around them of hot gas. These regions grow as galaxies grow, and we end at a stage where the whole universe is hot. Okay. In fact, after this discovery, we were awarded 250 hours on one of the largest telescopes on Earth, a very large telescope, to confirm this. They said, go and look at 30 more quasars, get high quality data, and make sure you're right. And these are some of the quasars. They are really beautiful. You can see extreme Lyman alpha absorption, right? And then this has since confirmed that idea that reionization ended at that point. We still haven't understood when it started. We still haven't understood how it progressed in the early stages. Just one tiny success that we understand where it ended. Okay. Now I have the technology to explain to you how we can make some progress on the problem of how supermassive black holes form. Okay. I'll just quickly say this because this is really exciting. Which is, it turns out that I have been showing you plots like this. This is a spectrum of a quasar, and this is that Lyman alpha forest again that I have been talking about. Turns out that there is a part of this spectrum, which is this part, which is peculiar in appearance. And this peculiar part has a name. It's called proximity zones. The amazing thing is the shape of that peculiar part has memory about that quasar's past. So it can actually tell us how long that quasar has lived. Okay, and in fact, you can measure how long that quasar has lived, and you find that the answer you get is about 1,000 years or 10,000 years, which makes our problem worse because we at least had about 100 million years to grow those billion-year solar mass black holes, but now we don't even have that. We have about 10,000 years. So the problem is much, much worse. So a PhD student of mine, Sindhu Satyavolu, again a fantastic cosmologist, she is now a postdoc in Spain. She tried to find out ways in which we can evade this. How can we avoid somehow this 10 to the 4 year, this 10,000 year constraint? And she said, okay, I'll play with this. What if the black hole grows, stops, grows, stops, grows, stops? And I says, okay, she tried with this and it didn't really affect until she played with the period over which it grows and the period over which it stops. And she was able to hit upon a ratio which allowed her to let the black hole grow for much, much longer time without changing the proximity zone. In fact, this model worked. For the first time, we were able to explain these proximity zone sizes. Technical plot, don't bother to understand any detail. But the idea was now we evaded that 10,000 year mark. And the prediction was if you evade that 10,000 year constraint, then the quasars, the black holes, must have grown in a phase where they are hidden from us, where they are growing, where they are accreting, where they have that disk, but magically we don't see that disk. Then Sindhu asked, how do I hide the disk? I have the disk, I need the disk because the black holes don't grow without the disk. So how do I hide it? And she found 3 ways in which one could hide the black hole disk. And one of the ways, in order to rule it out, we are now running a large program called Cosmos 3D, where we use the James Webb Space Telescope for 384 hours to observe many quasars in a very innovative way. So either they will prove Sindhu's hypothesis right, or they will scratch that one option and then we will focus on the remaining 2 somehow. Okay, I should start winding up. Where are we now? I hope that some of you have got a sense of the 3 problems that worry us from the first billion years, which is that we have never seen galaxies form. When did they form? What created these galaxies? We have never seen supermassive black holes form. It's very hard to make them. How were they formed? What created them? And then when did reionization happen? And I want, one of the things sometimes what happens is when scientists talk about questions, people get the idea that these guys just don't find any answers. And when they give answers, people say, this guy just talks like he knows everything. So now here, I just want to make sure that neither of these 2 cases are right. These problems remain open, but I hope I have given you a sense that we have made some partial progress. For example, here we have known that the first galaxies show a detectable signal in the CMB, and we have actually built experiments to measure that. We have figured out ways and concluded that supermassive black holes must grow in this obscured phase where they are hidden from us. And finally, we have managed to figure out the point at which reionization ends. At least that much we have figured out. So what's next? Well, one is we still need to find the cosmic dawn. We haven't found it. So that's the agenda number 1. We have to chart reionization. We want to understand how it happened. We just have figured out when it ended. And then we have to also discover those first supermassive black holes, those hidden objects that Sindhu thinks should exist, right? How are we going to do this? I want to give you a sense of how this might be done. Theorists like me are going to cook up ideas, some random time in the morning, maybe this is how supermassive black holes could go. You write the equations and you calculate it using the largest computers on the planet. Okay, this is where I want to emphasize the necessity of these large supercomputers. I think in India we have a serious crisis that we don't have enough computing capacity compared to advanced countries. In fact, Indian scientists are dependent on Europe and North American computers for this. Without these, you cannot make these simulations that I showed. But on the data side then, once modelers have made these models, we need data to confront them with. The James Webb Space Telescope is growing really strong. This is the amazing project by the Americans. The cost of this is about 80,000 crore rupees, but it's free to use for anybody on the planet. You can submit a proposal, and if you get selected, you get time on the James Webb Space Telescope. These are expensive bits. I don't know if they are costlier than the IPL teams, but they are pretty expensive. Then there is REACH. REACH will give us some data. At some point, we will measure that cosmic dawn blip that I predicted. Hopefully, that will tell us when galaxies form. A bit in the future, if you talk to people like me, word you are going to start hearing more and more often in planetariums and newspapers and magazines is the square kilometer array. This is this telescope. This is a ginormous telescope being built by 10 countries together in Australia and South Africa. This is going to be the largest radio telescope that is ever built. It's so sensitive. The superlatives are really nice to quote in public talks like this. It can detect a mobile phone signal on Mars. Not only that, it can detect an airport radar from a planet 50 light years away. So it's really sensitive. So this is just one part. There are 500 such parts scattered around Western Australia where no one lives. It's an empty part of that continent. This is, I think, about 1,200 crores. So this is expensive science. This is about 12,000 crores, out of which India is contributing 1,200 crores. The next amazing thing that is happening towards solving these questions is this telescope. This is the Vera C. Rubin Observatory. It is being constructed as we speak on a mountain in Chile in South America. This will be opened just in a couple of weeks actually. And India is participating in this very nice project. And what is this? This is going to create a time-lapse movie of the sky over the next 10 years. This is going to have one of the largest telescope inside it. It's a fully robotic telescope. It will make a 15 terabyte image of each part of the sky, visiting the whole sky every 3 nights for the next 10 years. Just an incredible project. We hope to discover all these quasars, rare quasars here. Culminating in 2030s, this is another thing which I hope people get more excited about, are these absolute marvels of engineering. This is just, my mind can't comprehend that mankind can make such things. These are called extremely large telescopes. So this is one of them. It's called TMT, in which India is involved. So India is paying money. Many countries are coming together to build this. This is huge. This is like many cricket grounds wide. This is a 30-meter mirror, and it's going to see extremely faint objects extremely sharply. This is being constructed in Hawaii at the moment. So the idea I want to convey is that these big questions need big science. Before I end, I really want to convey this because I think this is not appreciated. It's really easy to be impressed by these great images, but the crores that go behind it and the hard work that goes behind it is often not appreciated. So we need powerful telescopes, we need supercomputers, we need years of effort, very ambitious work. And what I want to urge you to do is, people often have in India this fascination for science, but I would urge you to also develop a cultural fascination for science. I think apart from the fact that it tells us something about the universe, it also injects a lot of beauty in our society. And so I want you to think about, as we support cricketers and artists and filmmakers, the reason we pay them so much money because they add joy to our social life, because we enjoy a society which has cricket and films and artwork. Similarly, I want you to think a bit about science as a cultural product. And I want to say that scientists like me depend on public and private funding to build these new telescopes and supercomputing. This doesn't happen by just meditating under a tree. This really requires investments and hard work to build this infrastructure. What you should get from this is, there are many Indians who are doing these big things with really big ambition, and they really deserve your support. So I think I'll end. Before I end, however, I want to say just one last thing, which is that somehow every time I come to Bangalore, because of my surname, most probably the one question I get most often is whether I speak Kannada. And most of the people just start talking to me in Kannada. Many people here don't know that Kulkarni is a very common surname in Maharashtra, Gujarat, Telangana, and other states as well. Now, it depressed me that I don't speak Kannada, and I'm having to really say, people teach me Kannada, random phrases, and then I forget them, unfortunately. But it so happens, as it so happens, my most favorite poet in the world is a Kulkarni. And not only is he a Kulkarni, he has enriched both Marathi and Kannada language. He lived in the 12th century. He lived in what is now the Ahmednagar district. I think they have changed the name. His name was Jnaneshwar, and he's absolutely the greatest poet in the world, in my opinion. And he has this beautiful line where he says, to comprehend the boundless sky, one must match its open vastness. I think I'll leave you with that and stop here. Thank you. I don't know if we have any questions.
If you have questions, please raise your hand. I'll bring the mic to you.
In the early slides, you showed how old is each object which we are seeing now. Can you go to that slide,
Sure.
please? Yeah.
How old is which slide?
As in, we see, sun is 8 minutes old, and moon
Right.
is.
Sorry. No.
Yes, this one. Sun is 8 minutes old, but how can Mars be 12 minutes old? I couldn't understand that.
Yeah, I mean,
Thank you.
yeah, good point. Mars is on a weird orbit, and sometimes it's much closer to Earth than 8 light minutes. Sometimes it's a bit farther. So the average is what comes out to be about 12. Yeah, it's on the other side of the sun, then it's much faster. So it's an average number. Yeah, but sometimes it's much closer.
Hi. I have one question.
Yes.
It is regarding what you had talked about quasars at
Yes.
the dawn of cosmic
Yes.
time.
Yeah.
There was a hypothesis proposed a few years ago about the direct collapse theory,
Yeah.
where the gas does not form a star, but it directly collapses due to some reason, weird reason, into a black hole.
Yeah.
Has that hypothesis been ruled out completely? Because you showed one of those slides about the proximity and how you tried to fit the theory using that proximity best. So has that been ruled out or that is still in play?
Yeah, no, excellent question. That's a pretty technical question. Thank you for that. No, it's far from ruled out. In fact, that is turning out to be the favored hypothesis now. It is looking that that might be the only way to make black holes, this direct collapse idea, but it has not fully understood yet. More work is needed for confirming it. But it's actually the only idea that might work in the end.
So the follow-up question to that is that why did it stop happening in the current universe or 10 billion years? I
Yeah.
think that farthest that we have seen is 1 billion
Yeah.
where this has worked.
Yeah.
1 or 1.5 if I'm not, I might be mistaking it. So why did it stop after that?
That's precisely the puzzle. Yeah, absolutely. You've got it. I don't have the answer. Yeah, that's exactly the problem is. Yeah. If it were happening later, we could have seen, and then this would not be a problem.
Thank you for the session. It was nice listening to you. Actually, this question is by my friend.
Yeah.
He couldn't attend the session. So,
Yes.
so all evidence like redshift and cosmic microwave background suggests that Big Bang really did happen in the past. But are there any chances that it's wrong? I mean, it's a theory after all.
Yeah. So this is something people like to think about. Yeah. So I think maybe I'll say a few words. This is a very difficult question, unfortunately. We like to not talk about it too much, but I'll tell you something. I can see my cursor. Yeah, there you go. So we constructed this diagram, and notice that I highlighted these two gaps, right? There was this one gap, and then there was this other gap. This one gap here we talked about the whole time. I didn't say a single word, which is what your friend has now highlighted. Now, what's interesting is that the short answer to your friend is that we actually don't understand the physics of the universe at this point. The problem is the universe becomes so small, we simply don't understand how to do calculation at that point. So here what you will find is most people don't yet, we haven't sort of achieved the maturity level to work around this time, and the work that has been done is very speculative. People have many ideas. For example, string theorists, we have many great string theorists in Mumbai who have done amazing work near this point here, but this is at the moment certainly very speculative and work in progress. The other challenge here is, the problem is it's very hard to observationally probe this epoch. So it's not entirely clear how we would go about. Again, there are some ideas, but these are very ambitious and challenging. So I think the short answer at the moment is we don't understand much. At the moment, what we call is, when we don't understand something, we give it the name singularity. So at the moment, technically we describe it as classical gravity has a singularity. What it means is that we don't know. The closer we go to this point, the more clueless we get, and that's basically the short answer. So anything could happen. We will only know.
Okay, and another question. This is my question: is black hole really a hole, or is it a solid object? Like, if you can describe it.
No, so a black hole is not a hole. In fact, we could be falling into a black hole right now, and we would never know. So you can't see anything. For the person who enters the black hole, it's nothing. It's normal life. The person who is outside watching this person enter the black hole, that guy sees that this person is shredded to bits. So the black hole is a very strange object. Again, yeah, I mean, this really makes what makes black holes pretty fascinating. One can go on and on. Black holes themselves have a singularity like this inside them. So if you go very deep in the black hole, again, I don't have an answer. Most people don't have an answer. Again, many people are working on that. But the way you should imagine the black hole is it's a region in space from where it's very hard to get out, right? So that's the idea.
So it's not a hole.
It's not a hole. There's nothing happen. In fact, you will not be able to tell at all by any experimental means that whether you are entering outside or inside a black hole. You will not be able to say.
Thank you.
So I have two questions. From where did the name lambda CDM come from? And the second question is, if every black hole, if every galaxy has a black hole at its center, why does it have a different shape? Like there's so many different shapes.
Yeah, brilliant questions. Both are amazing questions. So I don't actually know the name of the person who coined lambda CDM. I don't actually know, but the way where it comes from is it's a short form. So the C stands for cold, the D stands for dark, and M stands for matter. So CDM is any universe which has lots of dark matter. And if that dark matter has very low temperature, then we think our dark matter has very low temperature, then it's a CDM universe. If it was, there are WDM universes, there are HDM universes, they are warm dark matter. What is lambda? Lambda is dark energy. Why is dark energy not called DE? Why is it called lambda? You can blame Einstein for that. He called it lambda. People had a habit of using Greek letters in early 20th century. We don't do that anymore. So now probably we would have called it DE-CDM. Maybe lambda CDM sounds a bit better. It's also called Big Bang cosmology. Maybe more people know that. Big Bang cosmology was actually a derogatory word used by a person called Fred Hoyle, who is my, what's the word? Academic ancestor, my supervisor. And Fred Hoyle was against lambda CDM. And he gave a radio talk interview in BBC, and he said this Big Bang, and he was actually, he wanted to demean it by saying that it's what kind of a bang happens in this theory, but it's stuck as a model. So some people call it Big Bang, but it's called lambda CDM. So that's the word. I don't really know. It's a good question. I should do some research and I'll give you the correct answer next time. Now, your other question was if every galaxy has a black hole, why are galaxies different? It's because what decides how a galaxy will look is not the black hole. The black hole is still not, there is a black hole inside the galaxy, but the galaxy still has much more material than the black hole. So other things decide what the galaxy is. So for example, Jerry Ostraker's idea was that the way galaxies happen is this cosmic web has intersections. And when things intersect, gas can flow along the cosmic web and accumulate at that intersection point. It's like the traffic intersections. All the cars accumulate and start honking. Gas accumulates and starts making stars. Now suppose the incoming filament are slightly tilted differently. Suppose it's not a rectangular intersection, then the galaxy becomes different. So it's these details which change the appearance rather than the black hole. But the black hole does actually have a very remarkable effect on the inner parts of the galaxy. So there you are absolutely right. How the inner part of the galaxy looks, and all the inner parts of all the galaxies kind of look similar as a result. So you are absolutely spot on. Well done.
Okay, Girish, one question on the cosmic background, the microwave background, right? We know 100,000 years, but why can't we see beyond that? Is it that we need more powerful telescopes to see the microwave background beyond that point, or that's just a wall and beyond that we are not able to, it's sort of like the start?
Yeah, so this is a good question. It's the same reason that we cannot see inside clouds. What happens is when we look at the cloud, what we are looking at is only the bottom layer of the cloud. Somehow there is light inside, but the light we cannot make out because the light is scattered away. It's the same reason why when we look at the sun, we see only the surface of the sun. We know that there is light inside, the photons are being created. We cannot see inside because they are constantly getting scattered. It's only after they emerge from the surface do they travel in a straight line like light rays for you to see. You know, it's like if I suddenly put smoke between me and you won't be able to see me. Whereas I would still have light shining on me and photons will be coming from me towards you, but the smoke would disperse them away. Exactly similarly, what happens is that at that point, the universe is so small and so dense that it's rather like a star. And so that actually is a surface of In fact, the technical name for that boundary is the last scattering surface. It's the last scattering. There is no scattering after that. So inside that, there are just so many scatterings that the photons can't come to us. We can't see the light at all.
So that means we will not be able to see ever what happens beyond that.
Essentially, yes, although there are some really clever ideas. So they are very interesting, again, very, what should the word be? Maybe futuristic, but there are ideas. There is some hope, but it's very little. For example, one hope is we think that under certain conditions, in that gap, gravitational waves are generated, which will create a pattern on the last scattering surface, which we might be able to see. Then there are similar ideas. If this happens, then, but everything connects it to that last scattering surface. It's like me trying to infer from the cloud what's happening inside, guessing it. Maybe this cloud has a lot of rainwater, maybe that is a dry cloud. I'm kind of inferring it, so that much there is a hope. Otherwise, it's pretty tough. Yeah.
Second question is, there are these big radio telescopes that you mentioned, and the one Reach also is in. So they are all in southern hemisphere, Australia, South Africa. You mentioned one telescope in Chile.
Yeah.
Is there a particular reason for that?
Yeah, most humans live in the northern hemisphere, and everybody carries a mobile phone, which ruins radio astronomy. Of course, now Starlink is potentially going to make radio astronomy impossible from anywhere. Right. But Australia and Africa are very empty countries. So there are large parts there where there is no radio. The mobile phone frequencies are right at where we expect cosmic dawn. So in fact, we have the current most sensitive radio telescope is actually in India, on the Pune-Nashik highway. If you travel, you will see these really majestic large dishes of the giant meter wave radio telescope. It's currently the best telescope. The problem is, Pune-Nashik, that area is such densely populated, and the mobile phones make it essentially useful. So nothing related to this science has been possible with that telescope because of human settlement. In fact, this is so sensitive. I remember I was talking to an American astronomer using a very similar telescope in Australia, and he said one time his observation was ruined because a flight going from Sydney to Johannesburg was reflecting TV signal from Perth into his radio telescope. So it's really you need a radio quiet environment to do this.
Hi, sir. Thank you for the wonderful talk which we had now. I just have 3 questions, which is first one, do we have any thermal mapping of the universe which has been done?
By which I guess you mean, is the temperature measured at different points?
Yes.
Yeah, the answer is yes.
Okay.
So the interesting thing about the universe is, so I was slightly sloppy with my language. If you improve that thinking a bit, what is interesting about the universe is that today the light in the when I say light, there is all the matter content in the universe are 2 kinds. One is cosmological, which came from the Big Bang, and then everything that stars produced and humans produce, etc. So we are talking about the cosmological bits.
Okay.
The cosmological light, namely the CMB, has one temperature, and the gas has a different temperature, and the dark matter has a third temperature. We know that as far as we can tell, dark matter has temperature of absolute 0, as far as we can tell. Light, we know very well, has temperatures of 2.73 Kelvin. That's what got the first Nobel Prize.
Okay.
Gas, the temperature is measured only by the Lyman alpha Forest technique. Here, it hasn't been possible to measure it everywhere, but it has been possible to measure it on a large number of points.
Okay, thank you. That answered my second question also. Going to the third question, how are these fluid mechanics and the thermal sciences are applied in the astrophysics?
Yeah, so that's a very good question. The way this is done, usually, I guess the short answer, a glib answer, is by way of mathematics. So imagine that I asked you to study the physics of the air in this room. Now, I tell you that, trust me, the air here behaves according to the laws of fluid dynamics. So fluid dynamics laws are very well known. They are mathematical equations, partial differential equations, which we know how to solve under many different conditions. And then what you will do is you will ask some experimentalists to measure something, like maybe velocities. You will put some tracer, like feathers or some such thing. And then what you will do is you will take these numbers as some kind of boundary conditions for your equations. So this is what is done essentially. What you do is, as soon as I say that it is gravity and fluid dynamics and radiation physics that is necessary, we know what the equations are. What we don't know is the terms in these equations. Some of these require measurement, but the interesting, the non-trivial thing is, as soon as you have the measurement, the equations tell you how they interact. The equations will tell you that, no, the air here cannot be 1,000,000 degrees Celsius because it breaks certain other things. It breaks the experimental fact of existence of human beings. And so I guess the short answer is you quantify your measurement and you plug that into these equations. Now what happens is, what is interesting is where you can take this thinking is, what happens if that doesn't work? When that doesn't work, that's where real fun of research begins. Because now there are two directions. Either your quantification was wrong or the equations were wrong. And then people do both, and then there is a scientific process by which they hope to achieve clarity on what is what. You probably want to speak in the mic because there are people on YouTube.
It just came out now. A small question is that we know that in fluid mechanics or in aerodynamics, we have momentum equation, which generally concludes with Navier-Stokes equation.
Yeah.
Is that used in any of the applications in astrophysics, or at any point, say for example, the accretion disk, which we talk about? So any one example where
very widely.
like,
In fact, what is funny is that the reionization simulation, I treat radiation as fluid. So the radiation follows Navier-Stokes equation.
okay.
So it's precisely that.
Sure, thank you.
Great.
Sir, so I wanted to ask, like, we know that the Big Bang happened 13.8 billion years ago.
Yeah.
So, like, do we know any place where it happened? Like, can tell it happened here?
Yeah, it happened here. So it literally happened everywhere. We know where it happened. It happened here. In fact, the notion of here-ness started from the Big Bang. So it literally happened here. There's no other place. It happened everywhere.
Sir, and one more question. You said that light is 2.7 Kelvin. Like, how do we measure that light temperature?
Yeah, that's a very good question. That requires some physics. So the way we measure is using the spectrum. So just putting a prism on the telescope and gets this is the brightness as a function of frequency. That is called a spectrum. Now it turns out that essentially you can think of it as being measuring it using its color. So I don't know if you have seen very hot, in ironworks factories or something, they heat pieces of metal and iron. It becomes really red. You don't have to touch it. You just tell it by eye that it's very hot because of its red. You take it to higher levels. So in fact, if you keep heating it, it will become blue, even hotter. So there is a connection between the temperature and the color, and that is how we measure it. That's a very good question. It requires some physics, but in fact, if I recall correctly, Einstein did not get the Nobel Prize for it, but Einstein and Planck used it to explain this connection using quantum mechanics. He famously did not get the Nobel Prize for that.
Sir, we do know that there is the Chandrasekhar limit for stars collapsing into black holes. But then how is it that black holes, grow to the size of 10 million masses without a limit? I mean, arbitrary limit.
Yeah, so that's a good question. So the Chandrasekhar limit says that the star has to be of a certain mass to become a black hole. Above it, it can always make a black hole. It's below that is the problem. So the Chandrasekhar limit is a lower bound. You will have a problem if you find a really small black hole. Large black holes, there is no problem. So for example, you make two stars, make them into black holes, you merge them, you get a new black hole, which is the sum of the mass of these two black holes. You keep doing this. And there is no limit to which this can be extended.
Thank you. Sorry for disturbing again. When we say the Big Bang, where did it happen?
Yeah, as I said, it
Yeah,
happened
I
here,
just got another
in
question
Bangalore.
on that.
All the big things happen in Bangalore these days.
So then when we say that we are looking into space back down the line for 100 billion years ago,
Yeah.
so then we are looking at the lights which are coming from that far, and then we say we end up finding out Big Bang. There was one image which was also showing. Then you also have direction there, and we are also looking at that direction, and you are also, does that conclude that Big Bang is still happening at some place right now, or what we are actually looking into?
Yeah, so I would urge you to, it's fascinating line of thinking, but I would urge you to control yourself because this can really go a bit astray. one thing I will say is this direction is not a space direction, it's a time direction.
Okay.
It's like I'm saying Big Bang happened yesterday. That direction remains available. Space, it literally happens everywhere because the whole universe is small, at that time a point. And so there is no notion of there versus here. There is only here and now at that point. And anything beyond that, as was asked by this person, is speculation.
Okay, thank you.
This is perhaps an engineering question. You showed an example of a massive aperture telescope being built.
Yeah.
So for visible light,
Yeah.
can do terrestrial telescopes have any advantage over, say, space telescopes? Like bang for buck wise, maybe it is
Yeah.
just cheaper. Because otherwise, why you are building it rather than not building space
Yeah,
telescopes?
so very good question, very appropriate question. So the answer is, at the moment, the economics is such that building big telescopes. So first of all, building big telescopes helps. It gives you more resolution, if I may use technical terms. It gives you more sensitivity. So now the question is where to put it, either to put it on Earth or in space. Now, Earth is typically bad because there is atmosphere, but then the Earth is good because you can go and do repairs. So space is very tough because sending such big telescopes in space hasn't been possible. I think the limit is JWST, which is 6 meters. So beyond that, it hasn't been possible to put anything in space. The cost is JWST is $10 billion compared to this whole 30-meter telescope is probably not that much. It's 25,000 crores or whatever. Now what is done but we still are left with astronomy, the atmosphere. And what is done is what is called adaptive optics, which is really a brilliant idea where according to the atmospheric turbulence, the mirror is adjusted to get you really optical performance. And what you people should know is that in the 30-meter telescope, behind that ginormous mirror are going to be these things called actuators, which will do the job of moving. What's amazing is that these are being made in Bangalore. So I don't know if they open it on Science Day or something, but there is a wonderful astronomer in Bangalore who is constructing this. And actually they beat China to the construction of that, which they really are doing great job of constructing these things. They will sit behind these mirrors.
Follow-up question to that. You said one problem is that we cannot build very large aperture optical telescopes, or we cannot send them to space.
Yeah.
But for optics, does synthetic aperture idea work? So we can have small telescopes, but that it can simulate the aperture of a larger telescope.
So synthetic aperture idea works. The answer is yes. There is actually an optical interferometer doing synthetic aperture on I think VLT in Chile. They have a synthetic aperture mode. But synthetic aperture is used in two ways. One is you just merge the photons coming from both apertures, in which case it's essentially a larger mirror. So that's essentially what is being done. The other is you actually interfere them and try to do this thing. The problem with that is that the wavelength is very small in optical, so you need a chronometer at that accuracy, and so that limits the approach. But it is done. It is possible. I think there is I forget the name, but there is an interferometer doing exactly that. But yeah, great question.
We'll take last two questions.
Okay, so if we assume we know the age of a particular galaxy, can we use the same knowledge we have about the evolution of life on this galaxy, like Earth, to assume that there is life on other galaxies and other planets?
Yeah, sure. But I guess the challenge is how would you show that you are correct? So yeah, you are absolutely right. If we know that one planet in this galaxy called Milky Way has life, it's maybe not unreasonable to expect that in each galaxy there is about one planet which has life. But then the question is, how do I tell if I'm right? And that's the great problem. People are working on this. I'm not an expert on this, so I probably shouldn't say much. But for example, the SK has a program to do SETI, this radio signal from advanced civilization, because it's I said mobile phone from Mars and all that stuff. So it would be a good telescope to do that. And then JWST is doing that by trying to measure gases that can only be produced by which we think can only be produced by advanced carbon dioxide or complex molecules. And they try to see if we can find that. But this is still done within our galaxy. For outside galaxy, the galaxy itself is so tiny, we cannot pick apart different planets and stars to actually do this. So it's actually such a fascinating question, but unfortunately our universe is just too big to make progress on that, unless the aliens visit us or something, I guess.
First of all, thank you for the amazing talk, sir. My question is that you mentioned Lyman alpha forest doesn't work at early times. Could you explain why it doesn't work at early times?
Yeah, it's not a very important reason. It's a technical reason, but it's nothing fancy. So what happens is the Lyman alpha line is essentially what happens is UV photon of a certain wavelength comes. And if it has the right wavelength, the Lyman alpha transition is triggered, and that photon vanishes, and something happens to the hydrogen atom. That is the process. Now it turns out this process can be actually described by quantum mechanics. This was done by a brilliant person called George Field at Harvard University, and he showed that what we know about this transition is that this is extremely efficient. As soon as a photon comes, the probability of this happening is extremely high. It doesn't take much for the hydrogen atom to absorb the photon. So this in technical language is called cross section. In fact, what I find always remarkable is if I place an electron here and an electromagnetic wave comes, the electron will interact with the electromagnetic wave because of laws of electromagnetism. Now you put the same electron in orbit around a proton, and again an electromagnetic wave comes. Again that electron will interact. But now the probability of interaction is 11 orders of magnitude more than the probability of interaction of a free electron. Just putting different environment around that electron completely changes its response. So this Lyman alpha transition is not the only transition. There are hundreds of transitions, but this Lyman alpha is amazingly efficient. In fact, if you had Lyman alpha eyes, you will see tons of galaxies, because most galaxies emit 60% of their energy in just that one wavelength, because all hydrogen atoms there are absorbing various photons and converting them into Lyman alpha and emitting them at this ginormous probability. Okay, so what does this mean? The Lyman alpha transition is extremely efficient. So even if you have just a tiny bit of hydrogen atoms, if you send Lyman alpha photons, they're gone. You need really, really small amount of hydrogen. The great thing about our late universe is that it's hot and ionized. Because it's hot and ionized, the amount of neutral hydrogen atoms are really, really small. As a result, they don't wipe out the spectrum of the background object. There are these individual spectral lines. But as soon as you go closer to the 1 billion year mark, when the universe is just a bit denser, just a bit more neutral, the number of hydrogen atoms is just a bit higher. Just that little increase, not too much. It's still an ionized and hot universe, but just a tiny bit higher amount of hydrogen atoms, it wipes out the whole thing because this Lyman alpha transition is. You can ask the question then, can people use Lyman beta? Yes, absolutely. Then people try to use Lyman beta. Then that fails at some point, then they use Lyman gamma. The problem with these things, however, is that this higher transition, the cross section is very, very small. So then those measurements are very bad. But that is the reason that happens. Now, this is again very technical. This is having to do with the fact that the Lyman alpha cross section is large, and we have just a bit more hydrogen atoms around that mark than we would have liked. That's about it.
So that concludes our question and answer session. Let's put our hands together to thank Professor Girish Kulkarni.